In the last problem, we looked at a case in which we only had an optimizing function and no constraint function. This is typically the case when we're able to express the optimizing function in terms of one variable, but it isn't always that easy. Here's another common example that tends to be a bit more challenging. Suppose you want to build a cylindrical can with no top that has a volume of 30 cubic centimeters. Determine the dimensions of the cylinder that will minimize the amount of material needed to build the can. Step 1 is to identify the optimizing function and the constraint function. It's pretty clear from the description that we're interested in optimizing the surface area using the information given about the volume of the cylinder. Recall that the volume of a cylinder is equal to pi r squared h, and in our case, the volume is given to be 30 cubic centimeters. To help you visualize the surface area of a cylinder, we want to cut it along its height. What we're left with is just a long rectangular sheet and a circle for the bottom of the cylinder. The length of the rectangle is the circumference of our cylinder, which is equal to the diameter, or twice the radius, times pi. We can take the individual areas of the rectangle and circle and add them together to get a surface area of our cylinder. Next, we'll take our constraint function, or volume function, and express it in terms of h so that we can plug it back into our area equation. After canceling pi and r, we have that the area is equal to 60 over r plus pi r squared. When we differentiate the function, we get 2 pi r cubed minus 60 over r squared. Since the derivative is undefined at 0, we technically consider it to be a critical point. But again, if we think logically about this problem, a cylinder with the radius of 0 is not a cylinder, so we find the 0 of our function and get the value of 2.21216 for r. All that's left is to plug the r value back into the volume function and solve for h, which gives us the dimensions of the cylinder that minimize the amount of material used to build it. We'll briefly check to see that our cylinder has reasonable lengths for the height and radius, and by doing so, we'll have finished the problem. Okay, to recap. Step 1, we want to identify what is being optimized. Here we want to consider whether or not a constraint function is needed to answer the problem. Drawing a picture can be helpful. In the last problem, we saw a situation in which we only need an optimizing function, and this was because we were given information regarding the height, which allowed us to express all the other dimensions in terms of strictly height. Step 2 is to arrange the equation to be solved for one variable. Step 3 is to take the derivative. Once you have the derivative, find the critical points and use the first derivative test to check for extraneous solutions. In the case of this example, we got a solution of r is equal to 0, and we know that this is not a reasonable answer because we can't have a three-dimensional object with any dimension equal to 0, otherwise it's technically not an object. Step 4 is to plug back our critical value into the original function. The critical value will allow us to optimize the function of interest.